Chapter 4 is a very interesting and useful chapter for us folks. We're going to cover a lot of ground in chapter 4. As you can see, there's 7 sections. It's one of the longer chapters in our course that we worked with. Chapter 4 has its own merits, but also it's a chapter that's used quite a bit throughout your calculus series and beyond, and also in your engineering courses. Polynomial functions are one of the most important class of functions for us. And in this course, of course, we're going to look at again the general structure of polynomial functions, and we are in particular, other than graphing them, we are in particular interested in section 6 and section 7. Again, every section in this chapter is important, has its own usage, and also one interesting fact about polynomial function is that they can be used to approximate the other types of functions, such as the transcendental functions. These are your logarithmic function, exponential functions, and all your trig functions, your hyperbolic functions, and so on and so forth. So very important category or class of functions. So we're going to actually begin with section 4.1, and we're going to start this by talking about polynomial functions. All right, so here what you're looking at is a polynomial function. Now, depending on the book, depending on the author, we can use P, as in polynomial, P of x as a notation for the polynomial function, or you just use the general function notation. And this is the general structure of polynomial expressions. They have to be in the form of an x to the n, in that form, to be qualified as a polynomial function. Notice each of these structures that you're looking at, each of them follow the an x to the n format. So for example, if I look at a1x, that's a1 x to the first power, where n is 1. You see that? Even the constant term, a sub 0, is a sub 0 times x to 0. So it is in the form, here's n here and n here, because x to 0 is 1. That is why, provided x is not 0 itself. And for the constant term, it doesn't have to be 0. X is not 0. So those become the terms of the polynomial function. Okay, now the a's, the numbers that are in front of the variables, the a's are called coefficients. These are real constants for us. And indeed, even x, the variable, is real. And we're talking in sense of real numbers. Right, real numbers, not that something is real versus it's not real. Well, in this case, again, in the sense of a number speaking, means the values of the variables can assume all real numbers on the number line. And so are the a's, and not all a's are 0. If all a's are zeros, you get f of x equals 0, which is the trivial polynomial that would represent basically the x-axis. Now, every polynomial has a degree. The degree of the polynomial actually plays an important role as one of the important characteristics of the polynomial. It is the degree of the polynomial that will give us a clue into the turning points on the graph. How would they turn? How many they could have at most turning points on the graph. We look at the graph of these in the next section, and then I'll tell you more about it. And also the degree of a polynomial tells us about how many potential solutions we could be looking at when we solve these polynomial equations. Now, the term a sub n x to the n is called the leading term. So exactly what is this term leading? Well, this term leads the extreme or the end behavior of the function. And we'll talk again more about those in a few moments. Okay, the extreme or end behavior of the function. So keep that in mind. And I want to emphasize the term of the polynomial are separated by a plus sign. So for example, let's say I have a polynomial 5x cubed negative 2x plus 4. Notice, by the way, a couple of things. The polynomials, usually in math courses, we write them in descending powers of x. That's what this means. You see that? The exponents are decreasing. So descending powers of the exponent is how we write them. There is exception to that. Some other textbooks sometimes, I mean, that's just by convention. If you write them the other way around, doesn't mean the polynomial is incorrect, because addition is commutative. So for example, x plus 5 can be written as 5 plus x. So it doesn't have to be in descending powers, it's just the way it is. Usually in statistics courses, especially in multiple regression, they write these polynomials in ascending powers, increasing powers of x. But in this course again, and in your calculus series and beyond, in general mathematics, we write them in descending powers of x. That was item 1. Item 2, not every term of the polynomial must be present of lower degrees. So for example, this is a third degree polynomial because the leading term, the highest degree term, has 3. And notice the x squared term is missing, right? There is no x squared term in here, and that's okay. You can think of 0 times x squared if you want to write it in there, but it's really unnecessary, and we usually don't do that. Okay? So just want to point those things out. And let's say for this one, what are the terms? Remember, terms are separated by plus signs. So that's going to be 5x cubed plus and negative 2x plus 4. And those are the plus signs we're talking about. So the terms are 5x cubed, negative 2x, and 4. Those are the terms of this polynomial. Okay, and now that I have the plus, I can change these pluses with commas, and those become the terms of the polynomial. Okay, now the domain is what all can x be when I have a polynomial expression? Well, x can be anything, and that's what the domain is referencing. The domain of these polynomial numbers are all real numbers, and that is why they are so useful, because you can plug in just about any x, any real number, and you will get an output for the polynomial function. Now the graphs, when it comes to graph of these polynomial functions, their graphs are going to be what we call smooth and continuous. So the idea of being, let me write that. So the graphs are smooth and continuous. Now in this course, again, because we are in a pre-calculus course, we simply tell you what they are, but the formal definition of smooth curves and continuous functions are given in your first semester calculus. Okay, so essentially for us, smooth, that means there are no corners in the graph, no corners, and no cusps. So what do these look like? The corner, for instance, looks like this. And there you go. Then this would be a corner point. Okay, or I could have something that looks like the absolute value function. Here's the corner points. Notice there's a sharp connection between the two segments of the graph. In this case, the right and the left side. The right and the left side of each graph. Okay, so that's what we mean by corner. What does a cusp looks like? A cusp looks kind of like this. There you go. This is a cusp. That's what that is. And then, of course, cusp is CU. My U look like an O. And there you have it. So the polynomial functions are not going to do this. Okay. Now the continuity, again, as far as we are concerned, continuity means when you graph these polynomial functions, you never lift your pen or pencil. There you go. That's what continuity means. That's a continuous graph. Example of graphs that are not continuous, for instance, I can have a graph that looks like this. have open circle. It may jump and then go like this and go like so. So notice there's a number of continuities, or I should say discontinuities here. Here I have a jump, what we call a jump. You can see the graph jumps as I go from left to right. You have a jump continuity, and then you have what we call for this one is infinite discontinuities. So you have jump discontinuities again, not continuity. These are example of discontinuities. Okay. So it is discontinuity. This would be continuous. So this is what polynomial function could look like. All right. Now, let's see what different degrees of polynomials could mean and give you example of different polynomials with different degrees. So if I have f of x equals 0, right, this polynomial function, which is just the x-axis, by the way, if you graph it, this one has no degree. Okay. If a polynomial function is just a constant, call it a, this one has a degree equals 0. And the reason, because I can write it as a times x to 0, and that's still a, and there you go. There is your degree. Okay. Then I could now increase the degrees. A first degree polynomial would be a linear function like this. This one has a degree equal 1, and there it is, right? So we usually don't put 1 on the exponent. That's why the degree is 1. And so on and so forth. So for example, a second degree polynomial that has, let's say, all terms would look like this. A sub 2 x squared plus a1x plus a sub 0. Okay, this one has a degree 2. So we call that a second degree polynomial. All right. Now, once we've talked about the general polynomials, let's talk about power functions. Power functions are very powerful. No pun intended. Power functions are one of the most important class of functions for us, and they're very useful and pivotal in your second semester calculus. Now, surprisingly, power functions are fairly simple. Simple yet powerful. That's how you like them. And there you go. This is the graph. Not the graph, but this is called a power function. And of course, n here has to be in natural numbers. 1, 2, 3, and so forth. Okay. Now, example of power functions, for instance, could be x. And usually we group the odd powers together and we group the even power functions together. And I'll show you in a moment the reason for that. But put these together and you have the entire class of power functions. Okay, now let's take a closer look at the behavior of these power functions. Okay, and for that I'm going to go to my graphing utility here. So let me pause here and jump to my graphing utility. All right, so here I am. Now I'm going to graph these functions. Okay, notice I have, by the way, here I have to the left I have x, x cubed, x to the 5th, x to the 7th. And then I have those with even exponents. X squared, x to the 4th, x to the 6th. It can go on indefinitely forever. But let's take a look at the graph of x. Remember, x graph of just f of x equal x. That was one of the graphs in our library of functions. And that is indeed a line that runs through the origin, right? This is f of x equal x or y equal x. It's a 45-degree line that runs through the origin. And notice how this line crosses the x-axis at 0, and there is a very sharp, well-defined crossing. It doesn't pause. It cuts right through the origin without bending. So it goes right straight through that. Okay, now let's take a look at the graph of x cubed here. Check this out. There is a graph of x cubed. Now both of these, by the way, are increasing function as you go from left to right on the number line. As you go from left to right on the number line, the graph of y equal x, or f of x equal x is rising, and so is this one, right? So is x cubed. Therefore, both of these are increasing. Now, very interesting, both of these functions go through point 1, 1. That's this point, right in here, point 1, 1. And both of them go through 0, 0, and both of them go through negative 1 and 1. Okay, so there you have it. 1, 1, 0, 0, negative 1, negative 1. Now let's bring in x to the 5th to this mix and look what happens. And there is a graph of x to the 5th. Okay, it's this one, the green one. The graph of x to the 5th also goes through those key points, 0, 0, 1, 1, negative 1, negative 1. Now, but look at how it's behaving in and around the origin. So again, the blue is x cubed, right? So it does go through 0, 0, but it doesn't go right through like the line did. It kind of bends, spends a little bit of time in the neighborhood of 0, and then ultimately it will go down in this manner. And notice beyond 1, by the way, beyond 1, the blue takes over the red line, and there you go. This is the red line, y equal x. This is x. The blue is this one, right? This one is x cubed. So it's going to surpass beyond 1 rather rapidly. It's going to rise very sharply. And on the left side, it's going to drop very sharply. Okay. Now, look at x to the 5th. That's the green one. That's this one. Well, the green one also goes through 1, 1 and negative 1, 1. Now, notice how it's flatter around 0. It's going to spend a heck of a lot more time in the neighborhood of 0 before it sharply rises beyond 1. And it even takes over the blue curve, which is x cubed. Okay, now look at x to the 7th. Boom. See? So hopefully you get the idea now. As the degree of that power function, odd degree power function, has to be odd for it to behave this way. But all of them behave the same way, don't they? The difference is how they kind of turn, how they turn in the neighborhood of the x-intercept. In this case, 0, 0. So the higher the degree, the more time it's going to spend in the x-intercept, in the neighborhood of that x-intercept, and then eventually it will rise and go beyond. And the reason for this really flattening is because between 0 and 1, think about a number between 0 and 1. For example, 1/2. When you do x cubed, well, half of x, when you have 1/2 cubed, that's 1/8. X to the 5th, 1/2 to the 5th, that's 1/32, right? So as the degree on the exponent, the degree increases from 3 to 5 to 7 to 9, the actual value of the function is decreasing. That only happens between negative 1 and 1, okay? But beyond 1, it's a different story. Then x5th, x7th become extremely large. But this kind of behavior is what we're really interested in. Now, we talked about the end behavior of all of these x cubed, 5th, 7th, all the odd power polynomial and power functions, odd powers. The end behavior means for large x values and very small x values. So think of as x goes to infinity, becomes very large. All of these power functions tend to go to infinity, right? Positive infinity. And all of them on the negative side, as they get smaller, 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 they tend to go to negative infinity. That's what we call the end or extreme behavior of the function. So there we've really hashed out the power function x, where n, the exponent, is odd. Now, I'm going to remove these. And let's take a look at now those with even powers, x squared, x4, x6. Well, x squared was one that was in our library of functions, right? Remember, we talked about the basic parabola. That was back in chapter 2. Okay. Now, there you go. This is the graph of the basic parabola, x squared. Again, this point is 1, 1 right in here, right? This point is 0, 0, and this point here is negative 1, 1. So we have point again. There we go. 1, 1, 0, 0, and negative 1, 1. Now look at x to the fourth. X to the fourth also goes through the origin, and not through it actually. I'll correct myself in a moment. Doesn't not go through it as in like there you go. See, that's what we mean by going through the line x cubed, or x. This is x cubed. See how it goes through it? Comes from one side, goes through the other side. In the case of, let me go back here. In the case of x squared, what happens, it actually, the graph does touch. It does touch it, but then it bounces from it. So if I go from left to right on the curve, notice how it drops. At 0, it touches, and then it bounces from it. And it does so in the shape of a basic parabola. Now look at x to the fourth. Well, x to the fourth does the same thing. It's going to descend very rapidly, and then it's going to flatten a little bit. It will touch 0, spend some time in the neighborhood of 0 here, and then it will bounce from it. It too will go through 1, 1. It too will go through negative 1, 1. And check out x to the sixth, and you can see kind of what's happening with this one now. So when the exponent is even on a power function, the general behavior is like a parabola. The key difference is how it approaches its intercept. For x squared, the intercept is touched and bounced like a basic parabola. For x to the fourth, that's the red curve, this one. It still touches and bounces, but notice how it's much flatter than the basic parabola. And x to the sixth, much flatter, and then rises. And just like the odd power functions between negative 1 and 1, the function is going to become smaller and smaller as you get closer to 0. That's why it falls below as the degree of the exponent increases. But then the end behavior, look at when n, the exponent is even, the end behavior, when x is very large, so think about x going to infinity, the graph always rises. So we say the function approaches infinity. And the end behavior on the left side, to the left of 0, for very negative, small negative numbers, also goes to infinity. All right, so let me just keep x to the fourth here for reference, the end behavior of power function with even exponent. X goes to infinity, x very large, y very large. The function value very large. And as it goes to negative infinity, the function value very large. Now look at x to the fifth. There you go, that's x to the fifth. Let's actually go x cubed, and there you go. For x cubed, the end behavior, as x goes to infinity, y goes to infinity. X goes to negative infinity, y goes to negative infinity. So those are marked differences between them. Alrighty. Now let's go back to our notes. Okay, the next idea here I want to talk about are what we call the zeros of these polynomial functions. So if I draw my x-axis here, the horizontal axis, and let's say here's the y-axis. Now I'm just randomly drawing these. And there you have it. Okay. So I have actually marked my coordinate system with this. This could be the graph of a polynomial function because it's smooth and there are no corners or cusps, no discontinuities, right? Now look at the extreme behavior, the end behavior. As x goes to infinity, the function approaches infinity. It means it just keeps rising. Okay. And on the left side, as x approaches negative infinity, means as x goes in this direction, look at the function. The function is approaching negative infinity. And that is what we call the end or extreme behavior of the function. Let me line these up a little better. Okay, so we have that. Now, and let me do the right side. Okay, so that for now is good enough. The other important aspect of this is the following. See, these are the places where the graph touches the x-axis, and in some cases goes through it, here, here, and here, and over here at the origin it touches and bounces from it, right? Well, based on what we just observed on my graphing utility, if the graph of the function goes through the x-axis, that means that x-intercept has some form of a power function that is even. If it touches and bounces from it, the x-intercept is going to have some kind of an even power. If it goes through it, then that x-intercept have a odd power. Okay, now these points where the graph either touch or goes through, doesn't matter for this. These are called the zeros of that function. So zeros of the function are usually used, usually shown with the letter C, ABC, C, or the letter R. Your author in the book we use uses letter R, and R here stands for root. That's why he uses R. Okay, the zeros are called like the root of the function. Okay, so here's one, there's two, here's another 0, here's another 0. Okay, so this function has 4 zeros. Okay, so what do we mean by zeros of a function? That means f at that value, the function is 0. That's why it's called the 0. This is what the 0 we are referencing here. Okay, notice the r's themselves may not be 0. Here r1 is not 0. Here r2 is, it happens to be a 0. So the 0 of a function is a 0 in this case. But in the case of r1, r3, r4, these zeros are not literally 0. There are other numbers other than 0. Okay, so if f at r equal to 0, then in this case we're going to call r a real 0. Okay, a real 0 of the function f of x. All right, and just judging from the graph that I have, we can also talk about r as r is an x-intercept. Again, x-intercept of the graph of the function, of the graph of f. Okay, so that's what r is. Another way to reference this work that we're doing, then x minus r, that binomial, is a factor. It will be a factor of the function of f of x. Okay. And finally, we say that r is a real solution. Real solution of the equation f of x equals 0. Okay, so these are the roles r play. So for instance, let's take a look at this example. Suppose in my example, the function f of x is x squared minus x. So if I factor x, I get x minus 1, right? And if I set it equal to 0 because I want to find the solution of this, then by 0 factor principle here, x could be 0 or x minus 1 may be 0, which leads x to be 1. So in this case, notice we have 2 zeros. So The zeros are 0 and 1. So the 0 could be 0, a 0 could be something other than 0. Those are the zeros of this function. That means, again, x minus 1 is a factor. And we can see that clearly in this equation. These are factors. Remember, factor means a multiplication. So 2 times 3 equals 6. 2 and 3 are said to be factors. Okay, as long as you have product of two things. So in this case, again, the zeros are 0 and 1. And we can say that R1 is 0, R2 equals 1. So those are the two zeros of this function. That means this function has x-intercepts that are at 0, 1 on the x-axis. And remember, for x-intercept, y is always 0 because the point is on the x-axis. Okay. Now, a factor that is repeated more than once, then r is a repeated 0 of the function. So let me write that. If a factor, for example, this one, x minus 1, okay, or x, either or. If a factor is repeated more than once, then we say that r is a repeated 0 of f of x. Okay, because remember, factors create zeros, and those are the r's. Okay, now if x minus is 0 to the m, if we have r is 0, so if x minus r to the m is a factor of the polynomial function f of x, then we say that r is a 0 of multiplicity m. So for example, let's say I have x, here I have f of x is equal to x cubed, x plus 4 to the 5th. There you go. Suppose that's the factored form. So the 0 that comes from x cubed, r, is 0. The 0 that comes from x plus 4, call it r1 and r2, is negative 4, right? The 0 is what makes the factor 0. All right. So in this case, r1, which is 0, has multiplicity. It has multiplicity equal 3. And the multiplicity of negative 4 is 5. It's like having 5 negative 4s. Negative 4, negative 4, negative 4, negative 4, like that. Okay. And we already, so that's all I wanted to talk about in here. We talked about the in behavior of the graph of the function when I use the utility. So we're done with that one. Now, the other thing that is interesting for the graphs of polynomial function, it has to do with number of turning points on the graph. So an nth degree polynomial function has at most, means no more than, could be less, at most n minus 1 turning points. Okay, so for example, suppose f of x is 3x to the 7th minus 6x4 plus 20. I just made some bizarre polynomial. Not bizarre, but kind of unusual because it's a high degree. This is a 7th degree polynomial, right? So n is 7. Remember, and the degree of the polynomial is the same as the highest degree term in the polynomial. This one, because n is 7, so this has at most 6 n minus 1. 7 minus 1. 6 turning points. And these will help us when we graph the function. It just adds another piece of information for us when we graph these functions. Okay, now something about this at most. Let's say another example. We already saw the graph of what x to the fifth looks like, right? Using my utility, graphing utility. Remember, the graph of x to the fifth looked very flat, and it looked like this, right? Well, how many turning points there is? What do we mean by turning point, by the way? Let's say I have something that goes like this. This is a turning point, right? The turning point is the transition from increasing to decreasing and vice versa. Increasing to decreasing. So there's a turning point. Decreasing to increasing. That's a turning point, turning point, turning point. So this graph has 1, 2, 3, 4 turning points. Correct? Well, how many turning points does x to the fifth has? None. See, it just comes here and goes through. It doesn't turn like, say, in here. All right. So this one has 0 turning points. And based on what I said up here, we're just saying what it could have. We say the graph of f of x, x to the fifth, could have no more than means that or less than. No more than 4 turning points though. Okay, no more than 4. Well, this one has 0, which is clearly a 0 is no more than 4. 0 is less than or equal 4. So 0 is no more than 4. Okay. And there we have this one. Now, let's take a look at how we can graph these now. Graph some power functions using transformations of our earlier work. Okay, I think we did transformation in chapter 3. So suppose I want to graph f of x equal x plus 1 to the fourth. Now remember, let's say call it g of x. The basic power function here is the fourth power, right? Ignore the 1. So it's x to the fourth, and we know what the x to the fourth looks like, correct? So x to the fourth, let me do it like this, so I can fit another graph next to it. So our basic power function is x to the fourth, and this is the graph of x to the fourth. Remember, again, using my utility, I graph these. It's going to be like a parabola, but only flatter, around 0. So that's the graph of x to the fourth. Good. There you go. This is x to the fourth. Now, x plus 1 to the fourth, you can write it as x minus, right? X minus -1. That makes it x plus 1 to the fourth. And then go back to chapter 3. We talked about graph of f of a. Let me see. We talked about these transformations. We talked about the constant multiple of f of x. We talked about f of x minus h. We talked about f of x plus k. Remember this kind of work that we did? So going back to that, if you look at f at x minus h, and that's going to give me a horizontal shift, right? And this one is going to have a horizontal shift. Let me see if I can quickly reference that. That was in our chapter 3. Let's see, properties, linear, or maybe chapter 2. Yeah. Graphing techniques. There you go. Remember? So this is back in chapter 2 where we talked about f of x minus h, a f of x, all of that stuff, see, is now building up. So x minus h, if you have a number within parentheses, then that will give you a horizontal shift depending on whether h is positive or negative, right? So you might want to go back and review section 2.5. That's lecture 5 that I've done for you. So let's come back to this one now. In this one, there you go. So we do have a horizontal shift, right? This would be a shift to the left, the horizontal shift to the left. So I'm going to go left 1, So this is going to be -1, and redraw that basic fourth power. There's my axis of symmetry, and there's the graph using transformations. Okay. Let's do another one. Let's do an odd power function. So suppose this time I want a graph. This time I'm going to do f of x equals go negative x minus 2 to the fifth. All right. Now the basic function here, g of x, is x to the fifth, and that we know what it looked like. We saw it about 30 minutes ago in the beginning of this video. So x to the fifth, the x to the fifth itself looks like this, correct? That's x to the fifth. Now -2, well, x minus h. So this would be your h, which is positive 2 actually. So I'm going to go to the right 2 units. So say that's 2 units. 1, 2. And then you redraw that green curve. Very flat, moves up, very flat, goes down. Okay, so at this point this is x minus 2 to the fifth, correct? Now the effect of negative in front, that would be the a f of x in my lecture 5. If a is less than 0, then you have a reflection, right? Reflection about the x-axis. And that's what we're going to do. We're going to reflect this about the x-axis, and the graph's now going to look like so. And there you have that. This is the final graph. This is the graph of f of x. Okay, using transformations. All right. And that should be good enough for this one. So we can graph these variation of power function using transformations. Now, next, let's take a look at actually now creating some polynomials here. Okay, so for my next example, suppose I want to find now a polynomial function. Okay, and let's say I'm going to give you the zeros with real zeros. Means these are the solutions I want to have for the polynomial. And my real zeros are -5, -2, 3, and 5, suppose. And I want the degree to be 4. Degree equal 4. Now remember the general form of this polynomial function, fourth degree polynomial function, is going to be a sub 4 x to the fourth, a sub 3 x cubed, a sub 2, and so on. Right? And that's the general fourth degree polynomial. Now, usually in this work, we're going to let the leading coefficient, remember this is the leading term, the first term. If the polynomial is in descending powers, that's the leading term. This is the leading coefficient. The leading coefficient is the coefficient on the leading term. We're going to let it be 1 always for simplicity. You can let it be 1,000, but for simplicity we always let that leading coefficient to be 1. Keep that in mind. Okay, so how is this going to work? Well, remember the real zeros. The real zeros are in the form x minus r. Okay, and actually that would be like the factor of x minus r would be a factor of the polynomial function. It's the factor of f of x. And we earlier, remember, we talked about different, how we called, there you go, right in here. See that? We called r so many different ways. One of them was this one. If r is 0, then x minus r is a factor. All right, now, because x minus r is a factor, then we can write them like this. We can say f of x is equal to, here's my leading coefficient, okay, and the remaining It's x minus r1, x minus the second real 0, x minus the third, and x minus r sub 4, which is the fourth real 0, right? Now, I gave you the zeros up here, so we can put them from left to right. So it's going to be x minus minus 5, that's x plus 5. X minus minus 2, x plus 2. And x minus 3, and x minus 5. See that? And there is your polynomial fourth degree in factored form. In factored form. And that's good for our work. You could do a pairwise, FOIL it, and then once you get FOIL, you get 3 terms here. You get 1, 2, 3 terms here. Multiply, distribute, combine like terms, and go through all that jazz. And then you can get this final polynomial form. But again, for what I'm doing, the factored form will do. That's the polynomial. Okay, now let's do something similar. This time I want to find a polynomial, okay, with real zeros. So let me start with that. Find a polynomial function with w slash, means with real zeros. Now this time I want to have -2, but this time I'm allowing for multiplicity. Multiplicity of 2 means I want 2 -2's. The other 0 is going to be 4 with multiplicity of 1. That means only 1, 4. And suppose I want n to be 3. That means a third degree polynomial. So the general form is going to be a, right? X minus r, well, x minus 4, multiplicity of 1, so that's just one factor. And x minus -2, the other 0, which makes x plus 2. Except this is now a 0 with multiplicity of 2, so I'm going to put 2 on that factor as an exponent. You see that? And of course, we always let the coefficient, leading coefficient, to be 1. Therefore, this is going to be x minus 4 times x plus 2 squared. Okay, and again, factored form for now is fine. It's fine. And there you have it. Now, again, if you let actually a to be something else, then the answer would work. So if you let a be 5, for instance, then the answer is going to be f of x is equal to 5 times x minus 4 x plus 2 squared. So there's not a unique answer to this kind of problem, depending on what you let a be. If you let a be 1000, then this number in front will be 1000. Okay, but all of these polynomials, regardless of the leading coefficient, will have the same x-intercept. The y values will be different elsewhere, but at x-intercept, they all will have y that is 0. Okay, now let's take a look at the other way, another example of another way of looking at this. This time, I'm going to give you a polynomial. Okay, f of x. I'm going to go 3x minus 7 and then x plus 3 squared. Okay, so let's see. What is the degree of this polynomial? Well, degree is 2 for the second factor, 1 for the first factor. Combine, you actually add those degrees. So this is a third degree polynomial because it has 3 factors. Okay, and what are the zeros of this? In factored form, it's really easy to identify them, right? So the zeros are 7 and not 3. Remember, x minus h. So at positive 3 is x minus a -3. So the 0 is -3. The other one, multiplicity of 2, is you count it twice because you have a repeated factor. Now, for all practical purposes, if you count a 0 1,000 times, that's still a 0 or a solution, whether we will count it once, twice, 3 times. But for now, just because we're going through these terminologies, it's important we talk about them. Now, let's take a look at as far as the graph goes. So we want to determine whether the graph crosses or touches. Okay. And keep in mind, if you have odd multiplicity, the graph crosses. Okay, it crosses the x-intercept, that is. Crosses the x-intercept. That's precisely what they will cross, the x-intercept. Okay, and if you have even multiplicity, the graph will touch, correct? The graph will not cross, it will touch, and indeed I'm going to add touch and bounce, right? Touch and bounce from x-intercept. Okay, the other one goes through it, it crosses it, and the even multiplicities will touch and bounce from the 0. Okay, so for this example I have at x equals 7, because the multiplicity is 1 for this. So at x equals 7, the graph will cross, right? Crosses the x-axis, and at x equals -3, it will touch and bounce from it. And we'll look at the graph of these in the next section. So here's the touch and bounce. Now let's talk about turning points. N, the degree is 3, so that means n minus 1 is 3 minus 1 or equal 2. So this will have at most, don't forget the words at most, means that but no more than that, could be fewer. At most 2 turning points. So it could have 2, it could have 1, or it could have none. Don't rule out 0 here. At most 2. So it could have 2, 1, or no turning points. And let me throw the end behavior now on this. We're getting ready to go to the next section where we actually graph them, and all of this information that I'm writing right now will help us graph these. The end behavior will be the same as a n x to the n, the leading term. Right? And what is the leading term here? The leading term is going to be the same as 3x cubed. Now, why is that? This is a third degree polynomial, right? Third degree. Because n is 3, right? The form is a n x to the n. So when n is 3, this is going to be a sub 3x cubed. And remember, a sub 3, this is the leading coefficient on the leading term. Well, that is your a, right? Remember, the number in front is the leading coefficient. And that's how I got the 3 here. That 3 comes from there. All right, so the end behavior of this function is going to be the same as, power function x cubed, and indeed 3x cubed. Okay, and it's, by the way, purely coincidental that this is 3 and that is 3. Okay, so don't generalize that. I could have 5x cubed if this was 5 instead of 3. Okay, so again, some coincidences happen when they shouldn't. This was one of them. So it's going to have the same end behavior of 3x cubed. And what does 3x cubed look like? Well, 3 is a positive. 3 is greater than 0. So there is no reflection about the x-axis. And here's your cube function, right? Forget the 3 times it. That will scale it. Again, we only look at in this light whether this a is positive or negative. If that was -3, we then would reflect about the x-axis, but we don't need to do that. Okay, so this, as long as it's positive, there's no reflection. So there you go. This is the end behavior of the function that I have up here. For extreme values of x, it's going to behave like this. So how do we write this for end behavior? X goes to infinity, x gets very large, the function goes to infinity. That means this part. Okay. And for the other side, as x goes to negative infinity, the function approaches negative infinity. And that's again what we label as the end behavior of the function. All right. Now, let's take a look at a couple of examples. Again, more example of this one. And if you're getting tired, you might want to pause the video because you know we're almost an hour into this, and take a little break and come back and watch these two examples now. So I have f of x equal to -2x plus 1/2 squared for this one. Let's go x plus 4 cubed. So let's go through the things that we just did. This is a 5th degree polynomial, right? 5th degree polynomials. The zeros are -1/2, correct, from here. Multiplicity of 2. And it's going to be -4 multiplicity of 3. Got those. Those are the zeros. Now, whether it crosses or touches at zeros. Remember, if the degree is odd, it will cross. If the degree is even, it will touch and bounce. So, at x equals -1/2, multiplicity of 2 even, it will touch and bounce. And we will use this information in our next video. So it will touch and bounce. At x equals -4, it will cross. And how it's going to cross? It's going to cross not like the line does, not this one. It's not going to cross like that. It's going to cross like x cubed. So it's just going to bend somewhat, bend a little bit. So this is not how it's going to do. It's going to behave like that. That's the kind of cross we're looking at. It will cross like the x cubed does. That kind of a crossing. Turning points, I didn't put that. So this could have n-1. What's the degree, by the way? The degree, again, how did I have it 5 here? How do we get the 5? That's when you add 3 and 2. The degree is sum of the exponents on the factors. So because this is a 5th degree polynomial, so it has at most 4 turning points. Okay, so we got that one. And let's finish it with the end behavior. End behavior. For end behavior, we look at the leading term. The leading term is made up of the leading coefficient. It's going to be -2. And the degree is 5, so it's going to be x to the 5th. You see that? Those two pieces of information are very crucial for us. There. -2 is the leading coefficient. 5th degree is the leading term. All right. So it's going to behave like this. So what does this function behave like? Well, x to the 5th. X to the 5th is going to be very flat, around 0. Right? So there's your x to the 5th. The -2 is less than 0, so there is a reflection actually. Got to be careful if that number is positive or negative. Reflection about the x-axis. All right, so if there's a reflection about the x-axis, that means there. This is the final graph. So it's going to behave as the extreme ends up to x to -2x to the 5th. Okay. In between, by the way, that's just for extreme behavior. Around here, it's not going to be the same. Between the zeros, it will behave however it wants to behave. So let's write this one. For this part, as x gets very large, the function gets very small. And for this part, as x goes to negative infinity, the function actually goes to infinity. All right, and there you have that. So we discussed the extreme behavior of the function. All right, and done with this one. Let me just do one more example. I just want to make sure that you're comfortable with what we're doing, because it's so important for your calculus classes. Negative 2 x squared plus 3 cubed. Now let's take a look at this one. What's the degree of this one? Well, you have x squared and it's raised to the third power. So x squared cubed is x to the 6th. So this is a 6 degree. Degree is 6. Okay, 6 degree polynomial. And notice I ignored plus 3, by the way. For leading term, this is all you look at. That's it. Don't worry about the rest of it. And for this one, a sub n, the leading coefficient is negative 2, right? So we're going to put these together for the end behavior. For the end behavior, let me write that. The end behavior of this one is going to be the same as negative 2x to the 6th, right? We combine the leading term, leading coefficient with the degree on the leading term. And what does the graph of x to the 6th look like? Well, I did graph that about 5-10 minutes into this video using my graphing utility. Remember, x to the 6th is going to be very flat, and it's going to look like that, right? That's x to the 6th. The negative, again, because it's less than 0, will cause a reflection about the x-axis. It's going to be very flat, looking like so. And out of this work, we just want the extreme behavior, right? That's all we want. For this part, as x gets very large, the function gets very small, goes to negative infinity. And so does on the negative side. As x approaches negative infinity, the function approaches negative infinity also. And that would be the end behavior of this one, right? Now, let's, again, these are just end behavior. Let's take a look at the zeros. For zeros, remember we said the factor equal to 0. That's the only 0 here happens when x squared plus 3 is 0. Now x squared, subtract 3 from both sides. X squared is negative 3. And right in here, I know that there is no real solution. That means there are no real zeros to this function. And the reason, when you square a number, positive, negative doesn't matter. It's impossible to be negative, right? Like negative 2 times negative 2 is positive 4. Therefore, that's how we know that one has no real solutions. Okay, so no real zeros. If there are no real zeros, that means there is no x-intercept for the graph of this function. The graph never touches or crosses the x-axis because there is no x-intercept. Therefore, graph never crosses, nor touches the x-axis because there are no x-intercepts. Those are the touching points on the x-axis. So what could the graph of this possibly look like? It's probably going to look very much like what we have in red. It's going to probably look something like this. And you can see that there are no x-intercepts. And here's the graph. The graph is entirely below the x-axis. It's most likely going to look like that. Okay, So there you have it. Sorry about the lengthy video, but it's for a good reason. I don't want to make the video too short by rushing through it just because to have a short video, because you can always pause, stop, come back and watch it, but you need to get the full information that's necessary in order to do this correctly. All right, everyone, thank you for watching. In the next section, we're going to look at, or the next lecture, we're going to look at how we're going to graph these polynomial functions. Until then, goodbye.